Hello everybody. This will be a brief tutorial on how to use Keras for transfer learning, fine-tuning, bottlenecking, whatever. So I think I will also upload this in GitHub so you can see it, but it's just more or less your instructional video to this topic. So for this, we're gonna use a library called Keras. So what is Keras? Well, in a nutshell, Keras is a high-level API for creating neural networks, and you can run it on top of TensorFlow, CNTK, Theano, and so on. And basically, let's say in TensorFlow you need to write your neural network in 100 line of codes. Here you can write it in like 4 or 5 line of codes, and it's very easy to create complex model without, lot of without a lot of code. So here's a brief example. Based on the website, you'd say, I want to create a model. You can add the model different layers. So dense basically means a normal hidden layer. The units say the number of hidden units. You can define your activation function and so on. And you can add and stack layers as you like. So here in this case, you add another one, softmax. Then you can compile the model. So you can say which loss function you want, what optimizer you want, in this case the stochastic gradient descent, and then you fit the model. So it's a very simple API. And why is it very particular interesting for this competition? Well, it has a very easy way to add pre-trained models, edit pre-trained models, and yeah, and we will look at this at right now. So basically, I will show you several things. First, we're gonna start with bottlenecking. So what is bottlenecking? Well, let's say we have a pre-trained model. So I have here's the architecture of a old image detection algorithm called LeNet. Basically, it starts with convolution network, then with an activate with a 10 H how's called 10 whatever activation function, pooling, convolution, and so on. And in the end, basically, it does pooling, it flattens the layer, has some fully connected um, collected layer, and then it does some classification. So basically, this part, the lower part, is more about feature extraction, and then the low layers, so you have the fully connected layers, and the softmax, this part here, is more regarding classification. So what you would do is when you would take a pre-trained model, put your, let's say, image in, and instead of like taking the softmax, so your label, you would just take the features. So I guess the flatten layer here. Why would you do this? Well, the assumption is very simple. You say that um, the model is very good in understanding basic feature extraction, like detecting lines, shapes, and stuff like that. And by extracting those features, you could then train your own model, like now like something similar to this with your where the softmax output is the same size as your um, image data set. So in this our case, we have 128 labels. We add our own layers, and as input, we instead of the image, we take the these features which we extracted. So that's the basic idea of bottlenecking. Now, how we can do this? Well, there's let's say the easy method, in a sense, easy to CPU GPU usage. So basically, what we do first, these are some imports, whatever, and then we just load our data. So we have some nice functions which we can use in Keras. One is the image data generator, and this allows us to um, load the data automatically from a folder. So I will show you how we need to sort the data so Keras can read it. So as you can see here, we have in our raw data one in our training folder 128 folders, and each folder represents a certain label. For example, if I go to the first folder, layer 1, I mean label 1, you will see all the label data of label 1. Now, this is just a sample of the data, so that's why there are not so many, but basically that's how it would look like if you put all this is the basic idea what you would like to achieve. So said that, you would have a folder like that. So in train, we would have had all those folders. And basically from this, it will make a generator for those images. This is very good because you can not also um, fill your memory completely. It will load the images as you need. Therefore, you won't have memory issues. But I think the main point is that it has some other features like you can define the batch sizes, you can shuffle the images, and you can also do some pre-processing with it. So in the image data generator, you can not also um, you can define a lot of things like rotation, zoom, and flipping, whatever, rescaling, all those nice things already implemented in Keras. So this will also allow us to, you know, save some time. So here I wrote here pre-processing function equals pre-processing input. So what I did here is I imported a pre-trained model called Inception. And in this Inception, you have the model, but also some functions called pre-process input, which is very important that you import. This is basically a function which takes the image and then do the pre-processing steps required for the model. So for example, some models require normalization and in a certain way, and it will do that normalization for you. Here I also defined, so that's basically it. You basically load the data from train. You say a target size. In this case, this model takes images of 299 pixels. And I wrote batch size of 1 and shuffled false. This is that I want. This is the reason I did that is because I want the just I don't want to do batching. I just want to go through each single image and just do the predictions because we're not training. So that's why it's batch size 1. Okay. So, but of course you can do batch, whatever, it doesn't matter in this case. So now what we're going to do is load the inception model, and we have some parameters which are very important. So if you load the base inception model without these two parameters, you will get the model with this, classification layers, which we don't want in this case. And this is very easy to solve. All we need to do is just write include top false, and then we need to define a pooling, um, some kind of pooling. So what you would get is most likely a convolution layer. However, you would like to do some pooling because this would be too big, I would say, most of the time. You could take it, of course, but this layer is bigger than the image, so I'm not sure if you're like winning any space. But what you can do is do some kind of pooling, so either max pooling or average pooling. And by doing this, you can, extract those features, and you have less features, basically meaning that you need to use less space. So we load our model, and then we basically run our generator to do predictions. So in this case, this number represents the number of batches, I guess, or the steps in an epoch, and basically this is just equal to the number of images because our batch size is 1. So we run this generator, and then what we get is, these features. So if we look at the shape of the features, we will have a 2048 vector long, um, vector, a 2048 long vector, which we can use. So this is a big, memory save. You can also save this NumPy array for later. And basically for 4,000 images, you have, I guess, right around, I'm not sure. I think it was around hmm, almost 1 GB of data. I think that's the case. I can actually check that very quickly. Yes, and by doing this, you have, I guess, around 40 megabytes of data. So you can easily fit all the images in memory if you have, let's say, 8 or 5 GB of RAM. So while we do this, so as mentioned, we extract these features, and now we want to create a model, but now with our own, our own layers and our own softmax. So we do this. First, we want to get the labels, so we can get the labels from the generator. This is why generator put classes, and we want to do one hot encoding. This is the reason because softmax, it's the output of softmax is, an array, right? So if you have like a softmax a layer with 128 values, then the softmax would be, 128 values, and each values is 0, 0 between 0 and 1, right? So I hope you know those things. So what we need to do is do one hot encoding so we get the right label representation. And now we're gonna create a model. So we define a sequential model. This is how Keras API works there. And we add first a dense layer with 128 units. Relu input, we want to take, those features, so 2048. We will add also a dropout layer. This is the reason because we don't want to overfit, and you can add the dropout layer too. So of course you can experiment. This is what you can do. You can, read some blogs regarding this, but basically it's if you have like so many units, it's not a big issue if you add a drop. Maybe not so such large value, but you get the basic idea. And then you compile the model. And what I do is, the last function would be categorical cross entropy. This is in our case. And as optimization, I just took the standard stochastic gradient descent. And then I basically fit the model. I also put some validation set just to get an idea how the loss function is regarding validation. And I just ran this for 10 epochs. So, but of course you can run it for how many epochs you want. And finally you can save the model if you want. I added a link here. You can check that out. Now this is a model which doesn't take so long to train. The only long part would be just, calculating, predicting the features. This doesn't take not so long as the second method which I present, because in the end of the day it's just predicting, and you can run this also on CPU. This won't be such a big issue. Now the second method is a bit different. So it's basic, yeah. So in this case, I will do an hover model. So you can see just to see how easy it is to add another pre-trained model. So in this case, I use ResNet. So again, you have the ResNet, and you also need to import its preprocess input. Again, I load the data. I do a image data generator. However, in this case, I change the target size to 224 pixels because that's the size which is needed for the model. Basically, if you just look at the documentation, it's already written there what size you need to, so it's not like I just know it by heart. You can just check it out. Because we are training, we want to shuffle the data and add a batch size, so I did this. So to improve training, and then I will define the model. So there are different implementations of ResNet trained on different data. We just take the ones trained on the ImageNet dataset, so the weights from it. And then again, as previously, we just won't include the top. And in this case, um, I will do my own pooling. So because we are training on the model, we just, I just make it here in my own average pooling. And to get the output layer, you just write base put output. So I get it previously. And this is also another way to write, to create a model in Keras. You just write here the previous layer, and then here you write your current layer, and you basically stack those up in a variable. Okay, so I've got x with average pool with my average pooling, and then I pass this x then to a dense, so a normal full connected network, and then finally I added another full connected network for a softmax, which is the size of 128. And we create a model. To define an input, you just write the base dot input, right? So this is for the output, this is for the input, and as output we want the predictions, right? So very straightforward. And here comes the magic. So what we want to do is freeze the models, the layers. So what we can do is, instead of backpropagating all back, we just say, okay, these layers, so the layers which are not part of the classification classification part of the model, we just freeze them. So we won't train them. We don't backpropagate. Um, we don't, update the weights for them. We would just do it for our, classification part of the model. So we just say, this is very simple to do in Keras. You just say, you go iterate through the layers and say they're false. And in this case, we just want the pre-trained model part to be free. So this is very easy. We just go through every layer in the base model and just say they're trainable to false. We compile the model and we fit the model. And then this takes a longer time. So for my I have a GTX 1060 6 gigabyte version, and it took 62 seconds to run one epoch on this sample. So it would take actually on the whole data set half an hour to do one iteration. So it takes longer. But you get more information when you're trainable. So it's a bit better, let's say a bit better. But yeah. And then you can, after you did train your model for like, you don't need to train it so long, so you just need to train it for like several iterations. That's the beauty of it. There's, because the model is already quite well trained, you just, just to tune it a bit. And then you can do your predictions. So in this case, I did one little prediction on an image, and so I just took from this random image, not random, I just took from the first label, the first image, right? Load it in. These steps are necessary if you take if you take if you want to do it for one image. So basic, I'm not going to explain this too much, but basically that's a nice thing to have an image data generator because these steps are already done for you. And then in the end I get my X, right, and then the pre-processed one, and then I just do predictions. So we can see then the performance. So I can check so one thing to mention is that this generator has a downside, and this is not a big deal, but basically if we generator class indexes, so basically it maps every folder name to a um, to a to a label. So basically, it does like uh, categorical labeling, right? So if the folder is called one, the index is 0. So yeah, this is a bit annoying. You just need to look up this table. So in this case, if you want to see what's the label name of of the folder 1, well, in this case is 0, right? And now we check the prediction because it's softmax, we need to get the arc maximum, and in this case is 0. So in the index is 0, 0, so we have correctly predict the image. And of course, maybe you would do some, I guess, um, some put also validation set while training, whatever. That's all up to you. This is just the basic idea, and this yields better performance than the previous one. However, the big disadvantage that is it's more slower. However, you're not training the whole model at least. And now we come to next topic, which most likely we will do on the cluster, and this is fine tuning. So the fine tuning takes the idea one step forward, and is that, let's visualize this one more time. So we keep these, convolution layers, this magical stuff. We drop the fully connected path, so the classification part of the model. We put a new classification model on top of it for our own problem, and then what we do is just train the whole model, right? That's it. You train the whole model together. Now, ideally, you wouldn't do that. You will still limit the amount of layers you would train. So this is very easy to understand, maybe with an image like this. Let me see, CNN. This is wait, oh, that's not the CNN which I was looking for. Neural network maybe. So this is here's a very good example. So if you maybe this one, what you see here is basically you take an image, you use whatever subsampling, blah blah blah, and as you can see, when every layer in the convolution, you basically learn little features. So as you can see here, we detect lines, we detect whatever. Um, what I'm trying to say is that um, in the beginning it learns you don't want to remove the features which can detect like lines, curvature, shapes. Uh, Maybe not shapes, but just the lines and curves. You want to keep those, but so you don't want to train those because they're already well trained to detect those things. But I want to train the model to understand more high level features like how the shape of the object and stuff like that. So I hope that makes sense. But yeah, basically that's what we are trying to do. So um, okay, so what we're doing is we can print all the layers. And oops, this is markdown. I want this as code. And this basically prints all the layers in the model. And basically you would, find a point in the model where you would like, okay, everything before this we will freeze, and everything after this we would like to fine tune. And in this case, in this particular example of ResNet, they were, at least in the example given by Keras, they said, okay, after this layer, so convolution 2D 269, we would, you know, train it, and everything else before, we will just freeze it. And again, you do the same, you compile the model, and then you fit and you train it again. And yeah, that's basically it. Mm, yeah, so this again, it takes the same time or very similar, and but yeah, that's the basic idea. Mm, and then finally, you would do prediction on this model, and this most likely would give the best results. At least in practice, fine tuning gives good results. So, what are the next steps? Well, basically, it would be to to either wait for the cluster. No, but seriously, we could prepare some code in before, like write the code for different models, try to find where is the best point to cut the model. So in let's so I can give you example for inception, the inception model. So this is here I have a PDF all of the whole model, and basically there are a lot of like concats layers, so where they concatenate different layers together. And maybe you can say, okay, either I freeze it from here, or I either freeze it from there, whatever. You can define your freezing point somewhere here, and then train the rest for the fine tuning. So maybe you can do some research, maybe do some experimentation on a sample data, however you like. It's that those things we can really, take time and check it out. And yeah, um, just experiment, maybe go a bit deeper. Yeah, try to write the code for for our pre-trained models, but basically it's very easy. Just write, just I think I included a link to the end. Yes, so if you click on this link here, you will see all the pre-trained models, and even has NASNet, which is state of the art. So yeah, that's not so we have a good selection of pre-trained models without um, without a lot of without taking a lot of time to install them. So yeah, this is uh, this is it. I think was educational slash tutorial slash um, whatever. Okay, I think that's it. Thank you for your time and goodbye.